Hello everyone. In this video tutorial, we will explore the captivating realm of combustion modeling using ANSYS Fluent software. ANSYS Fluent is an all-inclusive tool for computational fluid dynamics with extensive capabilities for combustion modeling. If you are a student, researcher, or engineer seeking to enhance your proficiency in this area, this tutorial is designed for you. So let's dive in and get started. Combustion is a complex chemical process that involves the burning of fuel in the presence of an oxidant to produce heat. This process plays a critical role in energy production, propulsion, and heating in various engineering applications. For instance, the internal combustion engine, which powers most vehicles and many power generators, relies on the combustion of gasoline or diesel fuel. Similarly, gas and oil-fired heating systems use combustion to produce heat. However, combustion processes have inherent drawbacks. One of the byproducts of combustion is soot, which is a black, powdery or flaky substance consisting mostly of amorphous carbon. It is produced by the incomplete burning of organic matter. Another byproduct is nitrogen oxides or NOx, which are a group of gases composed of nitrogen and oxygen. Both soot and NOx are pollutants that can have adverse effects on human health and the environment. Engineers strive to optimize combustion processes to minimize the production of these harmful byproducts. Combustion plays a crucial role in power generation, acting as the primary process in the production of energy in power plants. In a typical scenario, a fuel source such as coal, natural gas, or oil is burned in a combustion chamber, producing heat. This heat is then used to convert water into steam in a boiler. The high-pressure steam is directed at the blades of a turbine, causing it to spin, which in turn spins a generator, creating electricity. This process is known as thermal power generation. Hence, combustion is the fundamental process that drives the production of thermal energy and, subsequently, electrical power. These phenomena can lead to fluctuating pressures on the blade surfaces, which radiate a sound. Understanding and controlling this noise is an important aspect of wind turbine design and placement, and it's an area where acoustic modeling can provide valuable insights. In transportation sector, the process is used primarily through the internal combustion engines of vehicles. These engines operate on the principle of burning fuel like gasoline, diesel, or biofuel in a confined space to produce high pressure and temperature gases. This energy is then converted into mechanical work, propelling the vehicle forward. Despite the rise of electric vehicles, combustion engines remain prevalent due to their energy density and existing infrastructure. However, they also contribute significantly to air pollution and climate change, leading to ongoing research and development to make combustion-based transportation more efficient and less polluting. In the context of raw materials, combustion is used to generate the high temperatures needed to melt metals, glass, and other materials in various industrial processes. It is the basis of operations for furnaces, kilns, and other equipment used in industries such as metallurgy, ceramics, and glass manufacturing. On the other hand, in the food industry, combustion is essential for cooking and baking processes. It provides the heat necessary for transforming raw food ingredients into consumable products. The control of combustion processes also allows for the fine tuning of cooking temperatures, ensuring food safety and quality. ANSYS Fluent is a powerful computational fluid dynamics software that offers advanced modeling capabilities to simulate fluid flow, heat and mass transfer, chemical reactions, and related phenomena. With respect to combustion modeling, Fluent provides comprehensive tools to simulate the complex physics involved in combustion processes, including ignition, flame propagation, pollutant formation, and quenching. It supports a range of combustion models such as premixed, non-premixed, and partially premixed combustion. Importantly, ANSYS Fluent can predict the formation and emission of pollutants like soot and NOx, which are critical for environmental and health considerations. Thus, ANSYS Fluent is a versatile tool for researchers and engineers working on combustion problems. Okay, let's dive into ANSYS Workbench software. Computational fluid dynamics has been revolutionized by ANSYS Fluent, which offers a powerful suite of software tools such as Design Modeler, Space Claim, and ANSYS Discovery. Also, ANSYS Meshing and Fluent Meshing. With Design Modeler and Space Claim and ANSYS Discovery, users can easily create, modify, and manage their 3D models with unparalleled precision and ease. These tools provide remarkable capabilities for geometry modeling, making ANSYS Fluent a game changer in this field. On the other hand, ANSYS Meshing and Fluent Meshing excel at generating high-quality mesh with advanced algorithms for precise simulation results. Let's enter the ANSYS Fluent software. And that's it. We can import our files using file import. And after a few moments, the case and data files are imported into the software successfully. Get ready to experience a wide range of mission options that will leave you spoiled for choice. With multiple options to choose from, you can select the one that perfectly fits your simulation needs and take your experience to the next level. If you're looking for top-notch mesh quality checking tools, you're in luck. They are absolutely fantastic and will give you a complete picture of your simulation's accuracy. For example, you can hit the check to check your mesh file and report the quality of your elements. With detailed insights into the quality of your mesh, you can easily spot potential issues and resolve them early in the simulation process. This means you'll have more time and resources to focus on what really matters, achieving the best possible results for your project. Are you ready to take your simulations to the next level? Look no further than Fluent. While the software is renowned for its advanced meshing capabilities, that's just the beginning. With Fluent, you'll have access to an array of powerful tools for visualizing geometry, mesh, and graphical results. You can check your boundary conditions in a way that is desired for you. By double-clicking on the Models option, here in the Task Page tab, we can see all the models available in ANSYS Fluent software. What we are going to investigate is the species model. Here is visible the species transport model is selected by default. This cutting-edge tool is designed to simulate the transport of chemical species within a fluid flow with incredible precision, with the ability to handle multiple species and their interactions, including chemical reactions, mass diffusion, convection, and thermal effects. This model is a game changer. Its applications are endless, from studying combustion and pollutant dispersion to chemical process engineering and more. We can define the properties of each species, such as molecular weight, formation enthalpy, and diffusion coefficients, and even explore reactions between species. With the species transport model, you have the power to unlock a new world of possibilities. After the species transport model, we have options for reactions. The species transport model provides various reactions to simulate different types of chemical reactions. Volumetric reactions occur within the fluid volume and are defined by the Arrhenius rate expression. Wall surface reactions occur on the wall surface and are useful in predicting material deposition or erosion on the wall. Particle surface reactions are used when simulating dispersed phase reactions, where reactions occur on the surface of the particles. And finally, the electrochemical reactions are used in the simulation of fuel cells, electrolysis, and other electrochemical systems. These reactions involve the transfer of electrons between species and are defined by the Butler-Volmer expression. Furthermore, there are three primary options for diffusion: diffusion energy source, full multi-component diffusion, and thermal diffusion. Diffusion energy source is an option that considers the energy source due to the diffusion in the energy equation. It's often used when the energy changes due to mass diffusion are significant, such as in combustion processes. Full multi-component diffusion is a model that solves individual species diffusion equations considering interactions between all species. This option is more accurate but computationally more expensive than the mixture average model. Thermal diffusion is a phenomenon where molecular species in a mixture respond to a gradient in temperature with a flux of particles. This option is important in high temperature gas flows and low pressure conditions where the thermal diffusion effects are significant. And then we have the mixture properties options. For example, here in the mixture material, you can select or define the mixture which is desired for you, or you can import a chemical mechanism. And under mixture properties, there are several options for turbulence chemistry interaction, or TCI, namely finite rate no TCI, finite rate eddy dissipation, and eddy dissipation concept. The first option, which is finite rate NOTCI, assumes that the chemistry and turbulence are decoupled and the reaction rate is calculated based on the molecular reaction rate alone. The finite rate eddy dissipation model is a combination of the finite rate chemistry and the eddy dissipation models. It assumes that the reaction rate is controlled by either the finite rate chemistry or the turbulence, whichever is slower. The eddy dissipation model is based on the concept that the rate of the, turbulence dissipation controls the rate of reaction. It's particularly useful for fast chemistry combustion cases. The eddy dissipation concept model is an extension of the eddy dissipation model, which includes the effects of local fluctuations in turbulence on the chemical reaction rates. It's suitable for simulating turbulent combustion where both turbulence and chemistry influence the reaction rate. The NOx model in ANSYS Fluent software is part of the species transport model that simulates the formation and reduction of nitrogen oxides, or NOx, during the combustion process. Here we have the NOx or NOx. In the first step, which is formation, there are 4 options in the pathways section. The thermal NOx is formed at high temperatures, typically above 2000 Kelvin, when nitrogen and oxygen molecules in the air dissociate into atoms and recombine into NOx. Prompt NOx forms in the flame front during the early stages of combustion from the reaction between nitrogen molecules in the air and hydrocarbon radicals. Fuel NOx is formed when nitrogen bound in the fuel is oxidized to NOx during combustion. N2O intermediate is a pathway where nitrous oxide is formed as an intermediate species during NOx formation. Also in the reduction tab, we have the reburn method. The reburn method in the reduction tab of the NOx model is a numerical approach used to simulate the reduction of nitrogen oxides during combustion process. This method is particularly useful in engineering applications where it's important to minimize the emission of harmful NOx gases. The reburn method works by introducing additional fuel or reburn fuel into the combustion system downstream of the primary combustion zone. This additional fuel reacts with the NOx produced in the primary combustion zone, converting it back into molecular nitrogen and thus reducing overall NOx emission. Next, we have the turbulence interaction mode. Here we have some options. The turbulence interaction mode tab provides several options for defining the interaction between turbulence and chemistry. The probability density function, or the PDF mode option, allows you to choose between presumed or non-presumed. The presumed option, which are the temperature or temperature species options, assumes that the fluctuations of species mass fractions and temperature are statistically independent, while the non-presumed option does not make this assumption. The PDF type also allows you to select the shape of the PDF with options including beta and Gaussian. The beta function is generally more accurate but requires more computational resources. The Gaussian function is less accurate but more computationally efficient. Lastly, the PDF points option allows you to specify the number of points for discretizing the PDF. This value affects the accuracy and computational cost of the solution. Here, the next option is the soot. The ANSYS Fluent provides several options for simulating soot formation and oxidation. The models include the one-step, two-step, Moss-Brooks, and the methods of moments. The one-step and two-step models are phenomenological models that represent soot formation and oxidation in a simplified manner, with the one-step model being the simplest. The Moss-Brooks model is a more detailed model that includes specific reactions for soot formation and oxidation. The method of moments is a statistical method that represents the size distribution of soot parts. I'm absolutely thrilled to talk about the powerful pressure velocity coupling schemes that this software offers. In the method section of the solution part, first up we have the simple algorithm. This iterative method is perfect for steady-state calculations, giving you reliable results with great computational efficiency. Next we have the simple C. It's a modification of the simple scheme, providing faster convergence and less under relaxation. It's a fantastic choice for dealing with complex flow simulations. Let's talk about the coupled scheme. The solver simultaneously solves the pressure and velocity equations, making it ideal for high-speed compressible flows. It's a game changer when it comes to handling challenging simulations. And finally, we have the piezo. This is a two-step method that first solves the momentum equation, followed by the pressure correction equation. It's a wonderful tool for transient simulation. Each of these schemes in ANSYS Fluent brings its unique strength to the table, providing you with a wide range of solutions for your simulation needs. Next, we need to initialize our project. The standard initialization method initializes the flow field by setting flow variables to user-specified constant values throughout the computational domain. This method is often used when you have a good estimate of the flow field. On the other hand, the hybrid initialization method initializes the flow field by interpolating values from boundary conditions. This method is particularly useful when you do not have a good estimate of your flow field. It can provide a better starting point for the solver, especially for complex flows leading to faster convergence. And finally, in the run calculation section, we can set the number of iterations, and after that, we hit the calculate. After the simulation is completed, we can see our residuals. And after that, we can extract some graphical results. For example, the contour. This contour shows the mole fraction of soot material. Here we can set our parameters. For example, the static pressure, density, velocity magnitude. You can zoom in or zoom out. Or move your contour using the pan option. Another parameters could be temperature, static temperature, or the mass fraction of, for example, C2H4, and other materials available in the solution. Also, there is patterns here. You can color the lines and select the realism from surfaces, which is the middle inlet and side inlets. If I change the color by option to, for example, velocity, that could be the result. There are vectors. We can define vector in the flow field, which is colored by the velocity magnitude. That's it. We can scale it, for example 0.1, and skip the number of vectors with the value of 10. While there are other options here in the vector options, custom vectors, and color map options. Okay, that's it. The simulation is done, and some results are extracted using the results section of the ANSYS Fluent software. And I hope that you have enjoyed this project.